virtual, but still extremely strong. Lou Fang is a principal engineer at who has been working on inference for a long time and has a long distinguished career in 3 degrees with a bunch of different places. Lou, can you talk to people? Let's test the tech. Sorry.
Yeah. Today I'm talking about how to evolve our recommendation system for info to support larger and more complex recommendation models. These days, models become more and more complex, and the model becomes larger and larger and very large demanding. We have a very new architecture to support. And then we're facing a lot of challenges. So today I will go through several major challenges and then talk about how to address them from infra perspective. The first challenge is how to provide good modeling applications. So, long time ago, at Meta, we use scalation. So people define a graph and treat the model and create inference fireworks. Most of the model engineers do like to define the takeoff model directly in Python because it provides great efficiency. But directly writing models in Python will not meet our efficiency requirements. Really, high efficiency requires graph representation. So with graph, we can do a lot of optimization, operator integration, model split, etc. And also pure C++ runtime can significantly improve the performance when you migrate a model from Python to C++. If the model is not GPU bounded, then here you can see at least 2 times improvement. Now the question is how we can capture the graph from Python program and become self-contained. So to achieve this goal, we developed different techniques in PyTorch to support multi-level graph capture. First, I would like to talk about is FX. This helps us capture the high-level graph, and then we can use this graph for transformation. On the left side, we can see that we define a model in PyTorch, very straightforward. And then we use FX model 3 to generate that model. And this is how this looks like. It contains function, module, and method. And then that means I can support different level of customization. For example, you can specify, hey, I don't want to trace into for linear. Then we can list this as a big module and we will trace it. And also it has a limited purpose for as it is symbolic purpose. The generation graph model is still defined in Python and good for model transformation and also dividing numbers. And with FX trace, we can achieve model capture for model transformation. However, it's still Python dependent. So we develop a for script and for transport. We further remove the Python dependency. For script and for export will generate some acceptance module. And then for export is lower, is something we are still heavily document. On the right side, it's an example how we generate a new exported program from regular PyTorch model. It's pretty simple. Another alternative is torch compile. Is that if user would like to do things like say not to graph export and with some Python support, then we can do torch compile that if some part we cannot directly compile, then we can go back to Python. This is good for trading and in some non-online inference cases, we can still use this technique. In addition, we have developed another language called Fortran. And in the Fortran, we deploy common modules to implement back factory and support implementing backs. And with such a deploy design, we can easily achieve a high-level optimization. For example, use embedded backs into single table backs and this domain library is defined in Python and also backed by highly optimized operator library FPGA. In the program, we have a native advanced Chandra support. That means it's very easy for us to further optimize and sharpen embedding back actions as long as we use Fortran library. Another challenge is that how we can scale the model size. In this case, model size is larger and larger. The common solution is that we apply compression techniques on top of the negative tables. The compression contains quantization and pruning. Quantization is widely used and can significantly reduce the model size by 2 to 8 times. Pruning is another technique that we remove some important rows from the model. And then with this technique, we may further eliminate the embedding size by 30 to 80%. Also, we develop hierarchical storage to support the large embedding storage. At the top, we have HTTP, and then it stores the most frequently used embeddings. And next layer is host memory. We use third large host memory to host embeddings. This is not stable. Then, based on the requirements, we may leverage the local SSD to store for larger embeddings. We also developed distributed storage like a cursor to support much larger embedding tables. Well, we stay in the model size. The main part of the model also increases a lot, which is the complexity of the model. So to achieve this goal, we have to support development techniques to accelerate the model. We have more and more model architectures. I can just do as mentioned in the previous time, the DHN, etc. The computation is much better than before. So we need new solutions to accelerate them, especially when we do real-time serving without acceleration. The previous software cannot be storing up support. So from hardware perspective, we leverage the new accelerators. I will talk about more details in the following slides. For example, have GPUs, we have NVIDIAs, and also we have the CPUs to support much heavier computation. From software perspective, we have different techniques that people need to do. We need to work with model owners to duplicate features and implementations. And also we can apply quantization and cleaning techniques in the dense part of the model. FP16 and BF16 is widely used, and FP8 is in the middle of adoption. We also leverage the competitors quite a lot. Inductor, which is part of PyTorch 2.0 effort, can significantly accelerate the dense part of the model. And the line inductor will support different backends, such as canvas, such as composable kernel, also Triton. They help us leverage or generate high performance kernels. We also use SRT, and also there is another framework data templates. All these are open source, you can check out. And as I mentioned, like new modeling, user can do feature and innovation manipulation. And from infra perspective, it also captures the graph, apply different type of optimizations, such as operator fusion within graph module or AI compiler. And the AI compiler and those high performance libraries can provide order and refresh. Another change is that we have larger and larger models and provide fresh models. Sometimes model size and freshness can be if you have a very large model, how can you load them on quickly in the sense? But who like to choose at the same time? The solution would be okay. That's upgrade the model without restarting the storage expense. We upgraded the weights on the fly. And meanwhile, because the model becomes larger and larger, especially the spark, depending on we cannot afford updating the full model and also between the checkpoints. There sometimes only a few rows are updated significantly, so we can just apply partial sparks like this. The main parts is how dance parts are uploaded, but they are pretty sensitive to the weights updates, so we have to do full dance updates. And right now, when we have creating system that uses updatable weights, we will send the partial updates to the burger server, and then meanwhile we will generate the dance weights and send it and load it in place. For example, we have a template, we have inductor and TensorRT which can support in-place updates. And the last topic I would like to cover is heterogeneous hardware. As I mentioned in the previous time, we have to leverage new types of accelerators to further boost the performance. We have new type of CPUs, we have new type of GPUs, and we also have processing, which is called training inferences. For more details, feel free to go check this. In Python world, actually Python itself can provide pretty seamlessly user experience for different hardware backend. For example, we can define a model, then that, and then we can just save this net snippet to the target place. Yeah, can define from the upstream devices. And now we want to load it to the GPU0. And then we just need to specify device, and then load the snippet to the target location. And we can also use this to move with a route that is move the route. However, this works well in the Python world, but in the C++, we need a dedicated user experience. So we also internally developed the support for such kind of improvements in the C++ environment. And we leverage PyTorch to hide the device details from end users. So they can just leverage this, like develop them on the target device, and then later we run it on different device. How we abstract these details away from users is that we just add more elements to define the model in Python word. And after that, users only see the model in Python word, and we abstract this away and export the model to the C++ environment using torch export and dynamo techniques. And then we generate the export environment. And another question would be, since we already have the model defined and available, and we have two high components, we need to develop different techniques and different hardware mechanics. The idea is that we like to provide same user experience as well, and abstract this common data as much as possible. So we leverage the component, which is inductor, triton, and then we have inductors for different backends, and triton has different support for different hardware backends as well. And then we generate artifacts using those two hardwares and pack them into the same model. So user will now know the details, and from the user perspective, you only see one PyTorch model, but we support different optimizations on different hardware. Yeah, that's about my talk.
Thank you very much. Very interesting project. Is there time for a couple questions?
Yeah.
Thanks a lot for the talk. Actually, in the model framing part, you mentioned about Delta update. I want to ask whether you evaluate the same during the Delta update. Is there any loss in model performance?
That's a good question. Depends on like there are two parts. So one part is sparse delta updates, and then another part is dense delta updates. And then sparse updates we use partial updates, and then dense updates we use in-place tool. And during our experiments, we don't see obvious loss due to the partial updates from sparse, and we didn't see any obvious loss from in-place updates for dense.
We have time for another question. So, my question is compared is also around those updates. I will switch it slightly. Can you talk at all about like how long that process takes, or the difference between when you're switching between doing the sparse and the dense, like that handoff seems somewhat tricky. Right? Can you go into is there any more color you can share there?
Yeah, sure. Um, for the next part, we have seen that